Hello YouTube, and welcome to Sidekick Studios, the channel dedicated to helping you get the image you want out of AI on your own terms. This is episode 3. In the last episode, I showed you what my AI imaging assistant, which I call Maya, can do. I showed you people who don't exist, photographed in worlds I imagined, but looking real enough that you had to take my word for it that none of it was actually taken with a camera. But as I promised you, this channel wasn't going to be about just showing you impressive images. It's going to be about explaining how any of this actually works. And if we're going to talk about that, we'll have to back up a bit. So today, we're going to explore the basic process of how your words are turned into pictures. Now, for some of you, this may be ground you've already covered. If so, I apologize, but I suspect that some of what I'm going to talk about will be new to a lot of people. Plus, in order to talk about how to really get the most out of AI imaging, we're going to need to understand how the process works. It might not be what you think, so let's get started. Now, the first thing to understand is the process itself. When an AI image model generates an image, it doesn't draw it. Effectively, it finds it. It's a bit like the old joke about the sculptor who makes a sculpture of an elephant from a block of marble by getting rid of everything that isn't an elephant. The process starts with random noise, just static, no structure, no content, and then it makes iterative adjustments, each one removing some noise so that the result is slightly closer to something that represents the thing your prompt described. Each step produces a result that is closer to the desired outcome than the last one was. This process is called diffusion, and that's how I'll refer to it. It's a version of an iterative search from noise towards a signal, and it's a technique that's been used in physics and signal processing for a long time. Now there it's normally called a fitting process. I know something about fitting processes because I spent years using them in my physics research. The principle is the same. You start with something unstructured and you iteratively constrain it towards a target until it converges on a result. The key word here is converges. The image isn't generated in one step. It emerges gradually through dozens or hundreds of iterations, each one becoming a little bit more coherent than the last. Convergence is achieved when further iterations do not measurably improve the outcome. So, the first mental model I want you to have is this. AI is not drawing your image, it is searching for it inside the noise, and it's guided to it by the prompt that you provide. Now, the other thing to realize, though, is that, in fact, AI does not actually make images at all. And that's because 1024 by 1024 pixel image contains over 3 million individual data points. Running an iterative fitting process across 3 million degrees of freedom simultaneously is, well, computationally impractical, even on the most modern hardware. And here by impractical, I mean time frames measured in days, weeks, or months, not in seconds. So even with the massive increase in computing power, a different solution is needed. And so we use something called a latent. A latent is not an image. It's a compressed representation of an image. Specifically, if you really want to know, it's a tensor, which is basically a vector, only more so. And specifically, it's a tensor with 16 channels at 1/8 the spatial resolution of the output. In other words, a 1024 by 1024 image becomes a 128 by 128 by 16 structure. Roughly 260,000 numbers instead of 3 million, or about 12 times smaller. And since the amount of computation scales is roughly 2 to the power of the degrees of freedom in the solution, this makes the problem about 4,000 times less computationally intensive, which makes it possible on modern GPUs. But this means that the diffusion process doesn't actually happen in pixel space, the world that you and I can see. It happens in latent space, which is a mathematical domain where the same information exists in a form that's easier to process. Now, if you've done advanced physics or signal processing, this might feel familiar. It's kind of analogous to taking a continuous signal and running it through a Fourier transform to extract its component frequencies. The result is not something you can see directly, but it is something that makes the mathematics enormously more tractable. You do your work in that transform domain, and then you convert it back. Now, in AI image generation, the thing doing that conversion is called a VAE, a variational autoencoder. It encodes your image into latent space before diffusion and decodes it back into pixels afterwards, so you can see the result. So, now that we understand how the diffusion happens and where it happens, but we haven't answered the most important question: how does your prompt, your natural language words, actually become an image? And this is a whole other story. And again, it's not all that straightforward, so buckle up. It's going to get a little math nerdy here. Your natural language prompt has to be converted into latent space as well. In effect, your prompt becomes a vector, which is a tensor of only 3 dimensions, right? Well, this vector is used to point or guide the model at every step of the diffusion, instructing it how to adjust the latent tensor towards a result that will look like what your prompt described when decoded from a latent into an image. Simple, right? So how does this conversion happen? Well, this is actually where most of the breakthrough happened and is happening. This is the actual artificial intelligence part. The fact that most of the work happened long before you typed a single word, you may not realize. The developers built a model like Flux, the diffusion model that I use. It did an enormous amount of work to make this possible. They took literally billions of images, transformed them into latents, paired them with natural language descriptions of those images, and then they fed those descriptions through a large language model. In Flux's case, the model is called T5XXL, for those who care, and that converted the language into mathematical guidance, and then they trained the diffusion model to associate that guidance with the visual contents of the images. Again, simple, right? What this means, though, is that by the time you type your prompt, the model has already learned from billions of examples what kinds of images correspond to what kinds of language. Your prompt gets processed through that same language model and converted into a guidance vector, and that vector steers the diffusion at every single step. So AI has to understand your words and then transform them into mathematics that is capable of finding the elephant in the piece of marble. So let's pull all that together into the actual sequence of steps that happens every time you generate an image. First, you pick a diffusion model, load it into your GPU memory. This is the core model, the thing that has learned from billions of examples what images look like when described by human beings. Second, you provide a natural language prompt. The prompt gets encoded through the language model into a guidance vector that will steer the diffusion. Third, and this is something we haven't talked about a lot, you may add your own low-rank adaptations to the tensor. These are called LoRa's, L-O-R-A, and if you want to apply them, they effectively become a special, limited, additional diffusion model that you train yourself, which inserts itself into the diffusion process and overrides specific aspect of how the model interprets your prompt. So instead of a model's generic idea of a woman with red hair, you get a specific woman with a specific face and a specific hairstyle. Trust me, I'm not going to spend a lot of time on it here because we are going to spend a lot of time on LoRa's in future episodes. For now, just understand that they exist, and they are how you get from generic results to the specific results you want. With that in hand, you create a latent that matches the dimensions of the image you want, and you fill it with random noise. This is your standard starting point. Then you get to the guts of the process. You run the diffusion, which is typically called sampling. There are actually several different sampling methods, and they can produce noticeably different results. We're going to ignore that complexity for now. It'll come up later. The sampling process uses the diffusion model to apply structure to the noise, guided by your prompt vector, iteration by iteration, until the latent converges on something coherent. At that point, the VAE decodes it back into pixels, and you see the result. Now, depending on the hardware, your hardware, that process can take anywhere from a few seconds to several minutes. This complexity is the same either way, though. You're just watching it happen faster or slower. All of which sounds complicated. Well, because it is. but it is something you can do with pretty modest hardware. For instance, I have an RTX 3070 Ti with only 8 gigabytes of VRAM, and I can use it to do this. Now, there are various ways to do this on your own machine. The one I use, and the one this channel will discuss mostly, is something called Comfy UI. Comfy UI was created by a developer known as Comfy Anonymous, strangely enough, who started writing the code in January of 2023 and published the first version on GitHub later that month. The motivation was straightforward. The existing interfaces for AI image generation treated the generation process as a black box. You typed a prompt, and maybe it gave you some settings, you got an image. Couldn't really see or control what happened in between. The philosophy behind Comfy UI was stated simply by its creator as, everyone is trying to make easy-to-use interfaces. Let me try to make a powerful interface that isn't necessarily easy to use. Now, this appealed to me because if you can see every step, you can understand every step, and understanding every step is what this channel's about. So what Comfy does is take all the mathematics we just discussed, the latent encoding, the text guidance, the sampling, the VA decoding, and it turns each step into a visible node in the workflow. You can see the model being loaded, you can see the prompt being encoded, you can see the sampler running, and you can see the latent being decoded back into pixels. It turns this multi-dimensional mathematics problem into something that looks and behaves pretty much like writing code. Each node does one thing, the nodes connect in sequence, the workflow is a pipeline, made visible. Okay, that's probably enough for today. I apologize if that went by kind of quickly. It isn't important to know much about how the math happens, really, but it is useful to understand what is happening as we go along. Because if we don't understand that, we won't understand how to change things to make it more like what we want it to be. Now, if you have any questions, or you think anything I said needs more explanation, or you want to add or correct or amplify anything I said, please leave a question in the comments. Thanks for listening, and I'll talk to you again soon.